All right, 3.9, day number 1, review of logs and the derivative of the absolute value of x. All right, so I want to start with a quick sketch. Here is the graph of y equals e to the x. Y equals e to the x. It has a domain of all real numbers. Okay, another way to write that would be negative infinity to infinity. Its range would be from 0 to infinity. Okay, now let's talk about its inverse function, which is y equals natural log of x, which has a domain of 0 to infinity and a range of all real numbers, right, or negative infinity to infinity. How are these related? Well, they're inverses of each other. So what is a logarithm? A logarithm is actually just an exponent. That's all it is. Why do they exist? So that they can undo exponential functions, allow us to isolate and find the answer for x. Right? So if you remember, let's consider y equals 2 to the x. Right? So if y equals 2 to the power of x, then what if y equals 8? Well, how do I answer that? How do I find out what x is? Well, I could, just know that x equals 3. If it's not quite so ambiguous or so simple, I'd do log base 2 of 8 would then equal x. Same thing if y equaled 16. Then log base 2 of 16 equals x. And same thing for 10. So if 10 equals 2 to the x, then log base 2 to the 10, log base 2 of 10 equals x. How do we evaluate that? There is no log base 2 button on our calculator, so we use the change of base formula. So if I have log base 2 of 10, that would be the same as, well, our change of base, let's throw that on the side. Log base a of b is equal to log base 10 of a over log base 10 of b. All right, now that's base 10 if you don't see a base there. I could do natural log too. So if I wanted to, I could do the natural log of 10 over the natural log of 2. Doesn't matter what the base is, but then I can put it into a base that I can use. So a logarithm is nothing more than an exponent. It is a way to solve an exponential equation for the exponent. A logarithm is the inverse of an exponential function. Okay, review here of the properties of logs. Log base a of a, well, a to the first equals a. A to what power gives me 1? 0. A to what power gives me a to the x? Well, that'd be x. Again, if these two bases here and here are the same, this will reduce to x. Product rule, this would be log of a, base 10, log of b. And we're going to add those. Over here I've got division, which is close to that. I'm going to do log of a minus log of b. Okay, let me work on the top down over here. I'm not sure why this is here other than just to make you think it's something other than it is. There is no special property to that. And actually, you know what, I goofed this piece up. This property applies to, gosh, I got fooled by my own deal there. This property applies here. This would be log of a minus log of b. All right, and then log of a over log of b would be the reverse of the change of base, which would be log base b of a. And you could go that way with it as well. Log base b of x to the r, what we can do with that r is bring it down in front. Okay, that's a property that's used commonly, okay. For example, the reverse of that, let's go like this. That's actually equal to log base 5 of 49, right? I bring this 2 up as an exponent. That becomes a 49. What is the natural log? Well, the natural log is just a log base e. We like to shorten it, call it the natural log. What is the natural log of e? Well, the natural log of e, what would that equal? Well, it would equal 1, right? Because this base raised to that power gives me that thing. What is the natural log of 1? Well, e to what power would give me 1? So the answer here is 1, the answer here is 0. Alright, we're going to find the derivative of the absolute value of x. Now, we're going to do that by taking y, right, and setting it equal to the square root of x squared. So the square root of x squared is actually equivalent to the absolute value of x. So let's say x squared equaled 9, right? If I took the square root of both sides, then I would get plus or minus 3 equals x, and wouldn't that equate to that? So technically speaking, we're going to take y, call it the square root of x squared, and we're going to differentiate that with respect to x. So of course what that would make this, it'd make that dy dx. And here, what I'm going to do is I'm going to take the derivative of this, I'm going to put it in power rule form. So I'm going to go x squared to the 1/2 power. Right? We don't want to simplify that by just negating those powers. What we want to do is we would take the derivative of the outside, so chain rule, and then the derivative of the inside now, and we're going to go ahead and simplify. So the 2 and the 1/2, they cancel. So I get x squared to the negative 1/2 times x. Now that will become, okay, I'm going to make this positive, so I'm going to bring that down here and change it to a square root, and therefore, recall from the beginning, what does that equal to? That's the absolute value of x. And there is the derivative of the absolute value of x. It's x over the absolute value of x. So let's use that same idea here with the absolute value of sine x. I'm going to rewrite this as the square root of sine squared x. And I'm going to go ahead and differentiate that implicitly. So dy dx, I'm going to do the operator over here. I'm going to call this sine squared x to the 1/2 power. I'll go off camera and come back in just a moment. Okay, so I did some chain rule and all sorts of good stuff in here, the power rule as well. And I got this long thing here, so I did the outside power rule, right? Took that to the negative 1/2 power. Then I did the next inner function, which is sine, or excuse me, the squared part of the sine squared x, right? Brought that down in front. And then the very inside, so I did a do chain rule twice, the derivative of sine x is cosine x. So these 2's canceled, sine x and cosine x stay on the top. I brought this to the bottom, making it a positive square root, and therefore the derivative would be sine x cosine x over the absolute value of sine x. Alright, that'll be it for 3.9 day number 1. We'll call that good for today. We'll move on and see you next episode.